Hi, now I'm going to talk about PN junction. Here, when we combine p-type and n-type, where what happens is in p-type majority charge carriers are holes, in n-type majority charge carriers are electrons. What happens is when they are combined side by side, electrons from negative on can move to p region and holes from p-type move to n region. That is negatively charged acceptors along with positive charged holes. So when they move, here a region is formed that is called depletion region, where no mobile chargers are there. So this depletion region's strength of electric field and how big is the depletion region can only be explained through energy band diagrams. Energy band diagrams for PN junction can be drawn as, first we consider this covalence energy and valence energy, and intrinsic Fermi of this energy is somewhere near towards covalence, and Fermi is somewhere near to the valence electron. When it comes to n-type, the Fermi energy is very near to covalence energy, and intrinsic Fermi energy is very near, is little far to valence energy. But when we draw a line, this is how the Fermi energy is constant throughout in p type and n type. So EF, when we consider this EF Fermi energy is constant at equilibrium, that is, and for p type, now we can take it as, see, the distance between intrinsic and between energy, intrinsic Fermi energy of p type and n type can also be added by the intrinsic energy of valence, the intrinsic energy of n type plus, sorry, the intrinsic energy of n type, intrinsic energy to Fermi energy of n type plus Fermi energy of p type plus intrinsic energy or intrinsic Fermi of p type. With both equations, for this it is kT of log Nd by Ni. That is doping concentration of a p type, n type. This is doping concentration of n type, that is Na, p type. So what happens is, for voltage is equals to, when we combine both, kT by Q log of Na by Ni square, or similarly equals to, we get a voltage of 0.7 volts given for silicon diodes. For germanium it is around 0.5 volts. Okay, this VBI is nothing but the voltage of that entire thing, entire junction is equal. From this, through we can get electric field as well as size of the depletion region. Now we talk about MOSFET operation, that is PN junction. See, for MOSFET we need to consider a substrate, that is p type. In there we just picked some space for n type. On n type we use some silicon dioxide for insulation, and from through n type we draw two connections, one is drain and one is source. These drain and source are not insulated. The only thing here insulated is, on insulated or the silicon dioxide we form a small gate contact. Okay, this p type can also be called as base or substrate. Okay, only gate is insulated from the substrate. These both n types in p substrate are highly doped. Highly doped is nothing but adding impurities. Now we consider operation of the MOSFET. In MOSFET, two PN junctions are formed. One is here and one is here. Here the PN junction is formed between P substrate and P substrate and drain source, drain of the FET, and this is reverse biased, and here again one PN junction is formed. Here it is between source and P substrate, that is forward biased. What happens is when we consider drain to a positive voltage, when source is connected to the negative voltage, that is DC voltage source, electrons flow from D to S. Okay. The channel will behave like N-type semiconductor even though if it is phi substrate. The channel depends on the strength of the potential given to the gate terminal. Okay. Due to electrostatic attraction, a conducting channel between drain and source is formed. Here, the channel is formed. So, the channel is called induced channel and the device is called induced channel MOSFET. If this gate voltage is greater than threshold voltage, this is threshold voltage, it is in offset. If gate voltage is greater than threshold voltage, it is in on mode. And this is when the gate voltage is driven by is connected to this positive voltage and negative is connected here. If the voltage is fixed, the current it is in it keeps on going. Here the current, what happens is in P substrate there are lot of holes. Due to the current passing, what happens is a virtual thing happens here which is not visible, which is visual. This here accumulation of the holes happens. When more voltage, if it is 0 volts, it will be normal. If we keep on adding the voltage here at the gate voltage, more accumulation of the holes happens and the electrons move through drain and source. Regions of MOSFET. In regions of MOSFET, if gate voltage is 0, is nothing but a cutoff voltage or pinch off voltage. If the gate voltage keeps on increasing, a saturation region is formed. In saturation region, the main factor limiting the current flow is the gate voltage, not the drain source voltage, that is VDS. Most application of MOSFET, we use them in this region, and if VDS is same as VGS, it is in saturation. Finally, if VGS is greater than or equals to VTS is greater than VTH, that is threshold voltage, electrons from source to drain flow in and form an inversion layer of electrons. The current of electrons connect the S and D regions. If we put V across voltage across drain and source, you will get a current that is linearly related to the voltage. Ohmic region or linear region or triode region. Triode because drain current of FET depends on voltage of MOSFET. Okay. If VDS is greater than VGS, the MOSFET will go into saturation region. So here a graph is drawn. It is taken across the different voltages like VDS, drain source to drain voltage, and it is on y-axis it is considered drain current. What happens is if initially VDS is applied, VGS is 0, nothing, current doesn't flow. So this is called cutoff region. What happens is when we keep on increasing VGS, even VDS is changing, the drain current increases not with respect to VDS but with respect to VGS. As it keeps on increasing, current also increases. So this part is called saturation region, and wherever from 0 to it is rising, that region is called linear region across different voltages. Okay. Thank you.